Suara saya terdengar ya?
Terdengar, Pak.
Oke, kita masih nunggu 5 menit lagi deh, masih 15 orang. Friksi, energi dari friksi, kemudian kemungkinan adanya energi potensial dan gravitasi juga, apalagi kalau aplikasi-aplikasi yang cukup ekstrim ya. Oke, sekarang ini saya karena kuliah yang di paralel internasional masih mempelajari PAM, jadi saya coba memperkaya materi dengan video yang saya ambil dari YouTube yang saya kira bisa memperkaya pemahaman ya. Nanti kalau ada pertanyaan silakan ditanyain. Oke.
Centrifugal pumps are used to pump water, oil, and other liquids. Let's try to understand why these pumps are designed to carry out the task of transporting liquids successfully. The main elements of a centrifugal pump are the casing and the impeller, which drives the liquid.
Sorry, ini oke ya? Enggak, videonya nggak kelihatan ya? Belum ya? Oke ya? Sekarang kelihatan ya? Halo?
Kelihatan, Pak.
Oke ya, saya ulang.
Maaf, Pak. Kayaknya nggak ada suaranya, Pak.
Nggak ada suaranya nih. Halo?
Di saya nggak ada. Mungkin
Yang lain
teman yang
gimana?
lain konfirmasi.
Yang lain ada suaranya nggak videonya?
Nggak ada, Pak.
Nggak ada, Pak.
Nggak ada. Oke. Ini gimana nih? Computer sound. Oke. Mana ya? Oke. Kalau sekarang ada suaranya nih? Ada? Halo? Apa terdengar suaranya, videonya?
Nggak ada kayaknya.
Nggak ada juga.
Belum ada, Pak.
Gimana caranya ya? Wait. Nggak ada ya? Kalau ini ada nggak nih? Ada? Nggak ada juga? Oh ini tadi ada nggak barusan? Nggak ada juga ya?
Nggak ada, Pak.
Nggak ada. Oke. Ada yang tahu nggak cara bantu ini? Ini apa? Memasukkan suara ya? Wait. Ini sel. Oke. Ini masih nggak ada suaranya nih.
Belum ada, Pak.
Nggak ada, Pak.
Nggak ada ya. Oke. Oh, ini ada suara nih. Halo?
Belum share screen.
Belum share screen.
How does the centrifugal pump work? Centrifugal pumps are used to pump water, oil, and other liquids. Let's try to understand why these pumps are designed to
Oh, tadi barusan ada suara ya?
Ada, Pak.
Oke. Sip.
carry out the task of transporting liquids successfully. The main elements of a centrifugal pump are the casing and the impeller, which drives the liquid. The impeller is mounted on a shaft.
Yang cukup umum
The
ya.
shaft can rotate on bearings. The power is transmitted from the motor, most often an electric motor, to the shaft.
Jadi ini ada bagian casing, ada impeller di dalam casing, ada bagian aksis shaft ya, ada bagian bearing, terus ada bagian electric motor. Ya.
The impeller of the pump rotates, together with the shaft. The vanes in the impeller act on the liquid and make it rotate. The liquid particles are accelerated. As a result of the impact of the vanes, the energy of the liquid flow is increased. The accelerated liquid particles enter the volute, which converts part of the velocity into pressure. The diameter of the passage section of the voltage and the discharge nozzle gradually increases. The fluid velocity decreases, and the pressure, according to Bernoulli's law, increases. Three main types of impellers are used in centrifugal pumps: closed with back and front discs, vanes and fairings. Semi-open with the vanes are free on the front side. Open with the vanes free on both sides. If bearings support only one side of the shaft, the pump is called a cantilever pump. It is a versatile design that is used in small and medium-sized pumps. A heavy impeller cannot be cantilevered. In this case, the shaft is mounted on bearings and the impeller is placed between them. This construction scheme is well suited for double suction impellers where the vanes are placed on both sides. A double suction impeller allows liquid to enter the impeller blades from both sides. Thus, we have two pumping units without significantly increasing the weight and dimensions of the pump. This scheme is relevant for pump.
Ini double suction ya. Ya, dibilang tadi bisa memperbesar debit tanpa menambah berat ya.
pumps with high capacities because the pumping units are installed parallel. Multi-stage centrifugal pumps. By installing pumps in series, the head of the liquid can be increased in the system. Pumps installed in series can be combined by placing several impellers in the same casing. The liquid will go from the first impeller to the second one, from the second impeller to the third one, and so on. Using a multi-stage arrangement can increase the head of the pump many times over, as the impellers are mounted in series, and each of them increases the head. In multi-stage pumps, different impellers can be used. For example, a screw centrifugal pump has an auger on the first stage and a centrifugal impeller on the second stage. When the pump is running, the liquid flows continuously into the pump casing through the suction nozzle. But what happens if there is no liquid in the pump? For example, when the pump is first switched on, the pump casing will be empty. For the liquid to fill the pump, the pressure in the pump casing has to be lower than the atmospheric pressure. Then, the atmospheric pressure will cause the liquid to fill the casing. To reduce the pressure in the pump, some of the air has to be pumped out of the casing. Is an ordinary centrifugal pump able to do this? The answer is no, because the particles move in the pump due to inertia, which depends on mass. The mass of air particles is much lower than that of water particles, so it is impossible to pump air at speeds that a centrifugal pump operates at. For this reason, centrifugal pumps must be primed before switching on, either through a special channel in the casing or through the discharge nozzle. If you are interested in rearranged pumps or other designs, let us know in the comment section, and we will try to make a video about them.
Oke, ini tentang animasi tentang centrifugal pump ya, yang cukup umum, mungkin dipakai di rumah kamu, di aplikasi yang lain. Ada pertanyaan nggak nih? Kalau nggak ada, next slide. Next video, sorry. Ini tentang positive displacement pump ya.
The main components of a gear pump are a static casing, meshing gear wheels, which rotate inside the casing, and a gland seal to prevent leakage of liquid.
Jadi pada video ini contoh dari positive displacement pump itu adalah ada gear pump, screw pump, scroll pump, dan vane pump ya.
Prime mover is an electric motor, and these types of gear wheels are often called spur gears. Gear pumps are employed on board ships for the transfer of fuel and lubricating oils. Gear pump consists of two meshing gears enclosed in a casing. One gear wheel drives the other. As the pump rotates, the movement of the gear first removes all air in the system, thus creating a vacuum. This is because there is very little clearance between gear teeth and casing, which prevents backflow of the air. After all the air is expelled, liquid is drawn and pumped into the discharge pipe. The liquid is transported circumferentially between the casing and the gear teeth and not between the two gears. The main components of a screw pump are meshing helical screws, an external drive gear, thrust roller races, pump body, and gland seal. Like gear pump, the screw pump has screws instead of gears meshed together. Both the screw shafts are provided with gears. One gear will drive the other, which will turn the screw, since they are on the same shaft. These gears are also called timing gears. As the screws turn, the trapped air in between the screw is pumped out to the discharge side. Air cannot flow due to small clearances between the screw and the casing. This creates a vacuum on the suction side and liquid is drawn into the pump. Liquid that is wrapped around the screw and the casing is transported axially to the discharge side. Screw pumps are often used to transfer lubricant.
Ya, jadi tadi gear pump, screw pump cocok untuk yang liquid yang viscosity cukup tinggi ya. Tadi ada oli atau fuel ya di kapal ya, ada MFO dan lain-lain.
Oil. It consists of a screw-shaped stainless steel motor. which rotates in a rubber stator having double internal screw threads. During rotation, the rotor tightens against the stator and the enclosed fluid is displaced axially through the pump. The center line of the pump moves slightly radially during rotation. Rotor and stator engage in such a fashion that it provides uniform positive displacement throughout the length of the pump. Also, the rotor and stator form a tight seal that prevents backflow of the fluid. This type of pump is versatile, as it can be designed to handle a wide variety of liquids. It includes liquids that are more viscous, slurries, pastes, solids in suspension, and even delicate fluids, largely because of the low flow velocities through the pump. Heads of up to about 45 meters are possible for each stage employed. Multi-stage pumps of this type are also used for deep well services. Vane pump consists of cylindrical rotors with slots in it. The slots have vanes that can slide in and out. The rotor is positioned eccentrically to the center of rotation of pump casing. As the impeller rotates and fluid enters the pump, the centrifugal force of the liquid pushes the vanes to the walls of the housing. The tight seal among the vanes, rotor, cam and side plate is the key to the good suction characteristics common to the vane pumping principle.
Okay, next is tentang cavitation ya. Oke, ini tentang kavitasi.
Welcome to e-learning in thermodynamics and fluid dynamics of our bachelor program in renewable energies and environmental technology. In this series, we are going over the phenomenon of cavitation in water and its consequences. What is cavitation? Cavitation is the rapid formation and collapse of vapor bubbles within a liquid. Such cavitation bubbles are formed mainly in locations within the liquid where the static pressure becomes smaller than a liquid's vapor pressure. The phase diagram of water shows if water is in its gaseous, liquid or solid state, depending on temperature and pressure. The horizontal axis of a diagram represents temperature, while its vertical axis shows pressure. The vapor pressure curve is part of a phase diagram. It indicates at which pressures and temperatures water evaporates from liquid to vapor or condenses from vapor to liquid. At a constant pressure of 1 bar absolute, water in its solid state, which is ice, melts to liquid water at a temperature of 0 degrees Celsius. Keeping the pressure constant at 1 bar absolute, liquid water evaporates when the temperature is increased above 100 degrees Celsius. Evaporation of water is not only possible when the temperature is increased at a constant pressure. The other possibility is to keep the temperature constant and reduce the pressure below the vapor pressure. Water can evaporate and condensate at temperatures below 100 degrees Celsius if a static pressure is low enough. This is exactly what happens when cavitation occurs. Bubbles of water vapor form when the pressure in a certain location decreases below the vapor pressure. The vapor condensates back to liquid once the bubble has reached a location with a pressure above the vapor pressure. But how is it possible that the pressure becomes very low in certain areas of a fluid? Let's have a look at an example for illustration. If objects, such as blades of a ship propeller, are moved through water, there is a higher pressure on the side facing the flow and a lower pressure on the opposite side. On other edges exposed to the flow, low pressure can also lead to cavitation. The bubbles collapse as soon as they reach an environment with a pressure above the vapor pressure. When pumps circulate water through piping systems, cavitation can occur where the pressure is lowest, at the inlet of pumps and in narrow pipe sections. If the pressure at the inlet of a pump is low and approaches the vapor pressure, cavitation can occur at the pump impeller as we have seen it at the ship propeller. The pump can deliver less water because the cavitation bubbles occupy a part of the cross-sections where the water should flow. Damage from collapsing vapor bubbles will be shown later. The same amount of water per time flows through the pipe with a large cross-section as through the narrow cross-section. Therefore, the velocity is higher in the narrow part and the static pressure is lower. The pressure is especially low at the exposed edge at the inflow side of a narrow part. We show a detail of a phase diagram of water, which allows to analyze the situation in a narrow pipe section. The temperature of a flowing water can be 20 degrees Celsius, which is a vertical line in the diagram. It crosses the vapor pressure line at an absolute pressure of 2,300 Pascal. As long as the pressure is higher, water remains liquid. If the absolute pressure decreases below 2,300 Pascal, water evaporates. The colors in the left visualization correspond to the colors indicated on the vertical axis of a phase diagram on the right. Upstream of a restriction, the static pressure is well above the vapor pressure. The static pressure in the flow decreases as the flow reaches the narrow pipe section. In our example, the pressure at the exposed edge is below the vapor pressure. Consequently, water evaporates and cavitation bubbles are formed.
Cavitation bubble terbentuk karena pressure-nya turun ya.
The low pressure at the exposed edge causes cavitation bubbles to form. At a pressure of 2,300 Pascal, a certain mass of water vapor requires over 50,000 times more volume than in its liquid state. The bubbles collapse as soon as they reach a region with a pressure above the vapor pressure. Because water from the vapor bubble occupies 50,000 times less volume after having condensed to its liquid state, the collapse of each bubble is a spectacular event and emits pressure shocks. Pressure shocks from many collapses result in an audible noise very characteristic to cavitation. The sound used now in the video has been recorded in an experimental setup similar to the one in the animation.
Tadi terdengar suara asli dari cavitation ya, di mana bubbles banyak terbentuk ya.
But how does it look like when cavitation bubbles are formed and collapse in detail? We can see the formation and the collapse of cavitation bubbles with a diameter of approximately 9 mm in slow motion. In real time, this process takes about 4 milliseconds, and it is a spectacular physical event. Because liquid water occupies many thousand times less volume than vapor, the bubble implodes. It first assumes a ring shape. Shock waves and a strong microjet are the result of a collapse. Let's go through the whole process again. If the local pressure decreases below the vapor pressure, water evaporates. A cavitation bubble is forming, is growing larger, and is transported with the flow to a region with a higher pressure. The bubble stops growing. If a local pressure exceeds the vapor pressure, vapor condenses, starting from the bubble's wall. Its surface starts to break down at its weakest spot. a microjet forms and pierces into the bubble's opposite surface. The bubble is now collapsing. The bubble becomes a torus and disintegrates further. The microjet continues to flow in the liquid and can hit a wall. Through its concentrated impact, even high-strength material can be damaged. The implosion releases energy in a very short time concentrated in a very small spot. If the microjet hits a surface, it damages the material by a localized short-term overstraining.
Ini salah satu impact dari collapsing bubbles adalah microjet ya. Microjet ini bisa crack sistem material ya, yang lama-lama causing the major damages.
The material starts to evolve microcracks, and later material can break off. We show a few examples of damage in pump impellers kindly provided by the Swiss pump manufacturer Herney. A brand new impeller to the left in comparison with an impeller having been continuously exposed to cavitation during 6 months, another impeller with damage from 12 months operation in cavitation, and one from 24 months. The new impeller shows the geometry as it should be under normal operation without cavitation. After 6 months of operation under cavitation, material has been eroded in the center of the wheel. The respective areas are highlighted with grey color. The impeller blades are undamaged. After a year of operation under cavitation, the damaged geometry has a different shape, and therefore the flow has a different pattern. The collapsing cavitation bubbles cause material break-off at the top edge of the blades. After 2 years, the blades have been eroded completely, which makes it impossible for the pump to function. In this video, we have shown the basic mechanism leading to the formation of cavitation bubbles, which reduce the flow of water. We have also seen the spectacular collapse of cavitation bubbles, leading to noise and damage even to high-strength material. Systems have to be designed such that cavitation is avoided.
Oke. Apa ada pertanyaan? Leo, are you there? Leo Agung Bayu Panuntun, are you there?
Iya, Pak.
Ada pertanyaan nggak tadi dari 3 video?
Saya belum ada, Pak.
Oke ya, jadi tolong perkaya, saya ambil dari YouTube gitu ya. Ada tentang cavitation, centrifugal pump, terus positive displacement ya. Nah, animasi bisa bantu kamu lebih memahami lah. Davin, Let Faza, are you there?
Iya, Pak.
Ada pertanyaan nggak?
Belum ada, Pak.
Jadi cavitation apa tuh? Bisa menyebabkan apa pada pompa?
Tadi kalau yang saya anggap bisa kayak merusak materialnya gitu.
Ya, jadi the collapsing bubbles create the microjet. Microjet ini walaupun kelihatan kecil tapi dia bisa merusak metal ya. Oke, ini video terakhir ini kita nanti di dunia teknik kimia sebagai process engineers ya deal with quite challenging project gitu ya. Kemarin teman kamu cerita ada kita punya pipa dari gas dari Sumatera ke Singapura gitu ya. Nah ini cerita tentang video tentang pemasangan pipa bawah laut, the longest subsea pipeline dari Norway kalau nggak salah ke Inggris ya, untuk pembangkit listrik di Inggris ya. Oke. Ayo. Oke ya.
It's one of the gas industry's riskiest construction projects ever. The longest subsea pipeline in the world. Giant ships lay 100,000 pipes linking Norway to Britain. Space-age robots trench an underwater moonscape beyond the reach of human hands. A project on this scale has never been done before. Will this survive the brutal North Sea? "120 kilometers off the coast of Norway is one of the North Sea's largest underwater gas fields. It's called Ormen Lange. At 40 kilometers long and 10 kilometers wide, and containing over 300 billion cubic meters of gas, it's simply massive. But it's locked in an icy tomb 3,000 meters below the sea surface, so deep and so remote that it's considered beyond the reach of man and machine. That is, until the engineers at Norsk Hydro, the Norwegian energy company, decide it's just too tempting to ignore. Because there is enough gas to supply 20% of Great Britain's gas needs for 40 years. The engineers know that in Britain there's an expanding market for natural gas. The coal they have traditionally been using to power their economy is no longer sustainable. The Brits are increasingly using foreign gas to power the turbines that create the electricity for their homes and factories, and they need more of it. So the engineers have come up with a plan. It will take 10 years and cost $10 billion. First, they'll drill the Ormen Lange gas deposit, transport the gas 120 kilometers to one of Norway's largest processing plants at Nyhamna, then send the processed gas to the UK down the Langelet pipeline, a staggering 1,200 kilometers. But to build the world's longest subsea pipeline this far and this deep requires overcoming some not...
Oke, ini subsea pipeline ya. Jadi pipa ini akan stay di bawah laut for the rest of this job ya.
So simple problems. They're drilling nearly 2,000 meters through the seabed to tap the gas field. And they'll do this with a rig built right on the sea floor. The real fun begins with this, the Storegga slide. The pipeline that brings the gas out of the field and delivers it to the plant has to scale this 300-meter underwater cliff face. And the seafloor terrain is too rough to lay pipe on, so that means trenching this monster. The gas itself is a dangerous mixture of debris and frozen water that could blow a processing plant apart, so they're adapting the system to handle the Ormen Lange gas. The plant is big enough to turn through 70 million cubic meters of the stuff each day. To handle this mega job, they've amassed some of the largest industrial ships in the world, each designed to tackle a specific phase of the deep sea construction.
Oke, ada yang tahu ini alat untuk apa nih? Kapal untuk apa? Ninyoman Gita Murti, are you there? Ninyoman?
Iya, Pak.
Oke, ini kapal apa nih? Barusan.
It's big enough designed to tackle a specific phase of the deep sea.
Kira-kira untuk apa nih, Ninyoman? Ninyoman, are you there? Nyoman?
Kapal untuk mengangkut pipanya ya, Pak?
Ngangkut pipa, dan ini apa nih? Ini pipa, ini ke bawah laut ya. Nah, ini untuk masang pipa di bawah laut, namanya pipelay barge ya, atau pipelay ship ya. Ini untuk masang pipa di bawah laut. Ya.
Construction.
Oke, makasih.
Out here in the harsh North Sea, humans are confined to the topside world. Beneath the waves, the brawny work is done by these underwater remote operated vehicles, or ROVs. They're a fantastic new breed of machines and are so technologically advanced, they're the stuff of science fiction. It's a monumental challenge, but with a pile of gas industry money behind them, the engineers can dare to dream. But are these guys going too far? Can they make this dream come true, or is this going to be an engineer's nightmare? First, they search the world for a gas well platform, which would work in these torturous seas. Existing designs fall short. The weather here is too stormy. The water too deep. Then, they suggest a revolutionary solution. If they can't bring the gas up to a rig, why not take the rig to the gas? Inside this warehouse in Tonsberg, on the coast of Norway, the key piece of solving that engineering challenge is being built. It's a daring move. The engineers are combining the function of a surface platform with a seabed drill guide. It's called a template, and it's an underwater gas platform that guides the drills through to the gas field and controls the well flow. Conventional gas platforms are sea surface structures, manned by an army of workers. In this case, the platform is dropped onto the seabed, clear of the wild North Sea weather. A drill ship then docks to it, and from above guides the drills through to the gas field. When the drilling is finished and the gas is flowing, the drill ship departs, leaving the template to control the wells. 4 of these monsters will be mounted on the seabed. Through them, a total of 24 wells can siphon over 70 million cubic meters a day from the gas field. The template will then direct and control the gas flow to a shore-based plant. The entire unit operating by remote control from a manned center 120 kilometers away. Richard Benyon is a subsea engineer.
The main thing that you've got, the difficulty that you've got, is it's dark, it's a devil of a job to put it in the first place. You've got to get this equipment onto the floor. It's highly valued, highly priced piece of equipment, and then you've got to put it together with robots, and you've got to make sure it doesn't leak. And apart from that, it's easy.
The stakes are huge. Engineers are building it to withstand pressures that would crush a normal submarine. And it has to operate flawlessly for over 40 years in a harsh saltwater environment. Once it leaves this warehouse and is lowered to the sea floor, there's no going back. It's going to be committed to the seabed forever. This 1,000-ton monster can't float on its own, so the structure is loaded onto a seagoing barge for transport to the drop site. With all the planning and building behind them, it's the weather that will determine if this mission is a success or failure. It's a 4-day journey to the drop site, and they've planned it to coincide with summer. It's the season of the calmest seas, which doesn't mean much here in the North Atlantic. They rendezvous with the world's largest crane ship, the Thielf, a super crane that does heavy lifts at sea. The 2 cranes mounted on board can lift over 14,000 metric tons. That's about 80 747 jumbo jets. The barge and Thielf wait for a weather window before lift operations begin. The contract to install the subsea components is worth $21 million. With so much at stake, they practice back on shore. The crane and ROV operators rehearse the drop. This is a 3D virtual underwater world, like the one they'll be working in. With weather, depth, and weight going against them, they practice. Now it's time for the real thing. Lines are connected. The record-breaking sea drop begins. This is their only chance. If they miss and it settles on the seabed in the wrong place, they'll have to build another one and set the project back by a year. Computer-controlled thrusters hold the crane ship over the drop site. As it goes below the surface, the underwater ROVs are put into action to take over as the eyes on the operation. They feed video back to the control room. The engineers scan the rig for problems as the pressure increases. From 1,000 meters below, the ROV feeds video back to the crane operator, who adjusts the orientation. They have to keep the ball bearing as close as possible to the center of the bullseye. He keeps the drop going, even when it's meters away from the sea floor. He's committed. There's no stopping it now. It's down, and it's so heavy, The legs on the base sink 8 meters into the seabed. But they won't know if they landed on the right spot until they check the coordinates. The reading shows it's within 40 centimeters of their target, close enough to be considered a perfect drop, accomplished from 1,000 meters above on a rolling sea. Now that the template has been successfully placed, the next step is to tap the gas field. It takes 2 years to drill the first 8 wells, and they must have them ready to go before the pipeline can be connected. A specialized drilling ship, the West Navigator, is moved into position over the top of the gas field. The Orman Lang gas wells will be the largest deep-water wells drilled in the world. They drill the field with a powered drill head operated from the ship. Once assembled, the pipe is lowered through the bottom of the ship and the 1,000 meters to the template. From here, the drill head moves another 2,000 meters through the seabed to the gas deposit. And then it snakes its way through the gas pockets. Every step of the way is monitored and recorded in a virtual database, which keeps expanding and is used by the engineers and surveyors to plot the next drilling spot. Back on land, the team can enter the cave, an amazing 3D undersea world. By virtually passing over the seabeds and the gas find, they can locate the most promising parts of the deposit. Jens Grimsgaard can plot the drill's movement from the cave.
With a joystick, I could also fly in this world by just using it, this tip here, and using my movements of my hand to steer myself through this reservoir.
During the drilling, data collected by the drill is sent back in real time to this database, which is constantly being updated. The computer generates the images.
Ya, ini proses drilling ya. Jadi dia ada drilling chip di atas tadi di permukaan. Dia coba mata bornya dicari mana yang paling efisien mencapai sumur gasnya ya, blok gasnya ya.
Which puts the team right in the gas deposit. They pinpoint spots from 10 kilometers away with astonishing accuracy.
That would be compared to that your dentist would be in the 10th floor, and you would be situated in the first floor, and he's going to fill out one of your tooths back there. We're getting extremely good results by doing this.
The template gets its power from the land through a 125-kilometer control cable called an umbilical. This cable...
Ini kira-kira kabel apa nih? Ada yang bapaknya kerja di offshore nggak? Kerja di oil and gas. Ini kok nggak pesertanya nggak ada namanya ya? Coba ya, ini NIM 50 siapa nih? 2050 siapa nih? 130250 siapa nih? Kok nggak ada nama, nggak ada namanya? Nggak ada nih ya? 050 nggak ada?
Lagi di toilet, Pak.
Ini kamu?
Bukan, Pak.
Siapa nama nih? Oh. 38 lah, 38. NIM 38. Siapa nih? NIM 38. 38, 41, 43 ada ya? Enam ada 66.
Ya, Pak.
Kemana kamu? Siapa nama kamu?
Saya Suha, Pak. Muhammad Farhan Suha.
Kok nggak ada namanya kamu di sini?
Oh iya, Pak. Habis ini saya lengkapi.
Oh gitu. Kamu lihat nggak ini film barusan?
Gimana, Pak?
Lihat kan ini, kamu video ini kamu lihat kan tadi barusan?
Iya, Pak.
Oh, ini yang kuning ini untuk apa kira-kira?
Untuk menyalurkan gas, Kak, Pak mungkin.
Bukan, ini kabel ya, namanya umbilical. Ya, ini umbilical untuk ngatur valve-valve yang di bawah laut. Tadi kan 3.000 meter di bawah laut ya. Ya, ini kabelnya. Nah, ini seperti tali pusar kalau di bayi ya, itu ada tali pusar. Nah, tali pusar ini di tali pusar kalau di bayi kan banyak, ada saluran makanan, saluran oksigen gitu kan. Nah, kalau ini juga ini si kabel-kabel bisa ngatur fiber optik, ngatur listrik ya, ngatur valve dan lain-lain.
Cable carries huge amounts of electricity.
Ini tolong dong diberi nama nih ya. NIM dan nama ya, biar ini. Ntar saya rekam yang nggak ada namanya nih. Part 1 50 ya, 59 66 91 ya, tolong
Enough to power 20,000 homes. Combined in this umbilical cable are tubes carrying hydraulic fluid, fiber optics, and electrical.
Nah, ini isinya nih. Isi umbilical ya. Ini ada pipa. Nah, ini ada kabel-kabel gitu. Ya, ini bisa isinya gas, bisa isi minyak. Nah, ini kabel-kabel ini bisa untuk menyalakan kompresor, menyalakan pompa di bawah laut ya. Itu deep water ya. Ini mungkin bisa 3 kilo dalamnya nih. Ya, bayangkan 2 kilo sampai 3 kilo di bawah laut. Ya, dari mana tuh? Dari ITB ke 3 kilo dari ITB ke Gasibu kali ya, Pak, dalamnya ya. Oh, lebih kali dari ITB ke BIP kali. 3 kilo ya.
Cables. The welds on these tubes have to be as strong as the welds on the pipeline. This is the power and control connection to the template. Without this, the template will be just 1,000 tons of useless metal at the bottom of the North Atlantic. But how do they deal with a cable that is a staggering 125 kilometers long? The cable is built in a factory right on the dock. As the cable is made, it is fed onto a giant spool on the deck of the Scandi Neptune. Once the 120 kilometers of continuous cable is spooled up, it will head out to the Ormen Lange gas field to connect the control room to the 4 underwater templates. But now, they have to prepare the seabed. The bottom of the ocean under the North Sea is a treacherous place. And, as you're about to discover, the engineers building the world's longest underwater pipeline are facing a mountain of trouble. 8,000 years ago, 2 pieces of Norway, each about the size of the island of Tobago, slid into the sea, causing a mega tsunami. The landslide, known in Norwegian as the Storega, created a huge shelf in the ocean's topography. The Ormen Lange gas field is on the edge of the Storega, locked inside the huge depression left behind by the slide. This underwater disaster created a mountainous seabed with peaks that rise between 25 to 55 meters. But the biggest concern for Hydro is how to get the pipeline up the Storega slide face, a whopping 300 meters. That's nearly as tall as the Empire State Building. Underwater surveys reveal a rugged and fractured seabed. But the unstable sediments have long ago disappeared. The rock is more than stable enough, and it would take a new ice age to dismantle it again. But the study has made them more aware of the seabed and the pathway they will need to clear for the pipeline that will connect the underwater.
Oke, ini lagi ngapain nih? Barusan Marcelino, Marcus Purba, 130280. Are you there, Marcelino?
Iya, Pak.
Ini video barusan lagi ngapain nih? Mau ngapain nih? Nih lagi mau ngapain nih? Sini.
But the study has made them more aware of the seabed and the pathway they will need to clear for the pipeline that will connect the.
Mau ngapain ya? Kira-kira?
Mungkin itu Pak nyusun kabelnya biar nggak nabrak-nabrak sesuatu
bukan.
gitu Pak.
Ya, ini untuk masang pipa di bawah laut ya. Dia cari bagian mana yang paling efisien ya gitu. Jadi nanti kamu tidak hanya teknik kimia tidak hanya mikirin panjang pipa, friction, tapi juga kamu bisa ngerti bagaimana masang pipa yang baik ya. Kalau ini dia harus cek dengan masalah gempa gitu.
The underwater gas rig to the land. First, they must build a 3D model of the sea floor and find the easiest route. What they have created is a virtual reality program. With this model, the engineers are able to plot the best pipeline route. The fisheries in the North Sea is a huge industry, and Hydro has to make sure the pipeline will not damage the reefs where the fish feed and the fishing boats work. But the concern is not just about the environmental impact at sea, but also on shore, where one of the largest gas plants in Norway is being built. The land connection they have chosen is the small island of Gossen and the tiny community of Nyhamna. The destiny of this quiet community will be forever altered now that it's been chosen as the landing area and processing plant for the Ormen Lange gas project. What was once a remote corner of Norway is being transformed into the bustling industrial center of the Ormen Lange gas project. Here, the raw gas from the Ormen Lange gas field will be converted into usable fuel. But to do that, over 2 million cubic meters of rock is being carved from the island, and over 30,000 tons of steel brought in. Almost overnight, what was once a small village has become the busiest construction site in Norway. Over 2,200 workers are on the job site each day to keep this mega gas plant rising from the rocky coastline. There's a canteen to feed 1,000 people in a city. Each night, the workers retire to the hotel, which will provide 1 million guest nights over the course of the project. But it will be removed. Three-dimensional models of the plant have been built, and the engineers walk through it in virtual reality before and during construction. Every bolt, high beam of steel, is pre-visualized. Because of the volatile gas, the specifications have to be executed perfectly. But the plant has been built for efficiency. The raw gas travels through the pipes and is converted into usable fuel in a mere 10 minutes. That's a blink of an eye in this business. Then it will be ready for delivery to the UK. The gas processing units are delivered to the island by ship. Cranes offload the components onto this massive flatbed transport. This remote-controlled monster has 48 independent axles and 96 wheels. It expertly shuttles the thousands of components needed to build the plant. Here on land, the workers have a close working relationship with the job site. But offshore, the workers hand in their wrenches for what else? Joysticks. Offshore, the underwater work is done with remote-operated vehicles, or ROVs, from pipe laying to heavy lifting. And that requires a lot of different ROVs and people who can operate them. In this warehouse is a simulation tank built just for offshore personnel to train on ROVs. It's driving school for robot jockeys. Here, they simulate projects that will take place.
Oke, jadi ROV gunanya untuk apa nih? Ada yang tahu ROV nggak? Fitria, Azara, 68, are you there?
Hadir, Pak.
ROV artinya apa ROV?
Enggak tahu, Pak.
Coba kamu cek di Google, ROV apa? ROV.
Remotely operated underwater, Pak.
Oke.
Oh, ini yang mesin ke bawah ya, Pak, buat ngelihat gitu.
Remote
Jadi
apa?
yang mesin yang buat ngecek ke bawah gitu, Pak. Jadi ada kameranya gitu, Pak.
Dan bisa masang pipa ya, dia bisa mengerjakan peralatan,
bisa memperbaiki gitu, Pak.
Ya, bisa melakukan servis di bawah laut, even dalamnya 3.000 meter gitu ya, dengan menggunakan semuanya dengan ROV. Kalau di udara ROV apa namanya? Kalau di udara?
Belum tahu, Pak.
Pernah lihat drone nggak?
Sepertinya bisa, Pak, kalau drone.
Nah, kalau di udara namanya drone, ROV itu. Tapi kalau di ini nih, di bawah laut ROV ya. Buat ngangkat kapal selam, mau cari kapal selam yang tenggelam atau mencari apa ini bisa dipakai ya.
Offshore. It takes special tactile skills to maneuver a crane arm from 1,000 meters away. Multiple cameras allow the operators to see the action. After the intense training with the ROVs, they're sent offshore, where the stakes are high and it's no longer a game. There are no second chances. This is the Pipeline End Termination Unit, or PLET, a big machine for one simple task. It connects the underwater template, or gas well, to the Orman-Lang pipeline. But it's never that simple. At 35 meters long and 30 meters wide, this 350-ton device is being lowered the 1,000 meters to the sea floor. Now that the PLET is on the sea floor, they assemble its components. Called modules, these components make the crucial connection between the template and the pipeline that feeds gas to Nihonga. All the connections at this depth are made with ROVs. But they can't do any of this work without first testing the systems. Thomas Berndt is the subsea manager.
We are testing and testing and testing here, and when we leave this hole, we are 100% sure that this connection will be tight when we come offshore. There won't be any leakage. A leakage offshore at 850 meters with large volumes of gas is a disaster, which we have to avoid.
They practice lowering the modules and testing the connections, which will be handling 70 million cubic meters of gas each day. They're training with an exact replica of the one that's on the sea floor. It's a large investment, but money well spent. Surrounding the connection module is a steel cage that protects it from stray objects that could drop off the drill ships and fishing trawlers. When the gas exits the field, the steel pipe expands. A little bit of expansion is okay. But the reason they're going to this much trouble is they expect the Orman-Lang pipeline to expand along its entire length by as much as 1 meter. And that's enough to rip it apart. So they've solved this by using a connector that slides back and forth on rails. It absorbs the pipe's movement and keeps the gas flowing. Meanwhile, the engineers are tackling the Storegga slide and trying to get the umbilical cord, or control cable, run from the template to the control center, 120 kilometers away. But to do this, they have to find a way through the rough and tumble terrain left in the wake of the slide. The solution is to build an underwater excavator, agile and strong enough to handle the job. It's a daunting prospect. That is, until they built the Spider. The machine that inspired this one was originally built for the Swiss forest industry. And like its Swiss cousin, the Spider moves along using powered tracks and articulated legs. Its mission is to excavate 6 trenches at water depths up to 1,000 meters. The biggest of them is a 4-meter wide by 4-meter deep monster trench, big enough to drive a truck through. One Spider is outfitted with a powerful shovel. It's strong enough to cast aside a 3-ton boulder. Instead of a shovel, the other Spider has a suction nozzle. Powerful water jets.
Jadi untuk pemasangan pipa pelatan bawah laut ini kadang-kadang mesti dibuat ekskavator bawah laut ya. Dia bisa ngangkut 3 ton boulder ya, batu kali ya.
Break up the sea bottom, and the nozzle sucks it up and fires the mud to the side. All the while, the Spiders will contend with slopes up to 35 degrees. There are sensors on all movable parts, connected through an umbilical from a support vessel, which floats above and monitors its progress. The umbilical carries power and control cables and lets operators manipulate the 6-meter-long spider to within 10 centimeters of accuracy, 10 centimeters from 1,000 meters above. It's an unprecedented mobilization of such complicated and agile robots. In all, these two champion diggers managed to excavate 3,500 cubic meters of soil, creating a safe path for the gas pipeline. The Langeland, which runs 1,200 kilometers from Norway to the UK, is the...
Berapa kilometer? Panjangnya, pipa gasnya, Gerard, Xavier, 69, ayo deh.
Halo Pak, hadir Pak.
Hey, morning. Dari Norway ke Inggris, kira-kira berapa kilometer tuh pipa bawah laut untuk gas? Barusan.
Bentar ya Pak. 1.200 ya Pak kalau nggak salah ya.
100 kilometernya dari mana kira-kira kalau di Indonesia tuh? Dari Banten sampai Surabaya atau sampai Banyuwangi ya? 1.200.
Wah kurang tahu Pak. Mungkin ya nggak tahu lah kalau di Indonesia sih kurang tahu ya Pak. Saya
ya itu mungkin dari ujung kiri Pulau Jawa sampai paling timur Pulau Jawa itu 1.200 kali ya. Nah, kamu bayangkan ini adalah dalamnya gas ya pipa. Yang kita pelajari di mechanical fluida ya kadang-kala quite challenging ya, bukan ekstrim, challenging ya, 1.200 km dan itu di bawah laut di North Sea yang climate-nya menantangnya, dingin, ombaknya juga ini. Oke.
Largest subsea pipeline in the world. This job requires 1/3 of the world's combined pipeline production capacity. That's over 1 million tons of steel. The value of the pipeline contracts is an unimaginable $700 million. Langeland uses pipes over 1 meter in diameter, and each single piece of pipe has to be able to stand the enormous pressure on the sea floor for the next 40 years. The pipes are each 12 meters long and weigh 10 tons. Another 10 tons of concrete and metal is added to give them enough weight to stay on the ocean floor. A total of 100,000 steel pipes are needed to span Norway to the UK. That includes over 1 million tons of concrete and 25,000 tons of steel reinforcing. Robert Payne is the man responsible for the integrity of the pipeline as it's being assembled.
Each joint of pipe weighs about 20 tons, about 10.
Ini proses preparation untuk pipa bawah laut ya. Jadi pipanya juga di-reinforce dengan beton ya, biar cukup berat dan stay almost 40 years in di bawah laut.
10 tons of steel, 10 tons of concrete. It's concrete and it's got inside of it a wire mesh foundation to help it stick together. There's so much volume inside of it whenever it gets on seabed and it gets light of air, it wants to float. So the concrete keeps it situated on seabed.
Each of the 100,000 pipes is numbered as it comes out of the plant, destined for a specific location in the line. As the team is trenching on the steep Starega slide, the rest of the route from the top of the slide to the shore is being prepared. This is the island frontier. It's a state-of-the-art trenching ship that combines two types of trenching methods into one powerful machine. They survey the flat areas where they think they can bury the pipe by scraping a trench through the sandy bottom. What they discover is not a pretty picture. The sandy bottom is actually clay, and the clay is hardened like concrete. A new digger is required to cut a channel up to 7 meters wide and 5 meters deep. The margin for error is only 50 centimeters on the width and a crucial 10 centimeters on the depth. The clay cutter hybrid, the only one in the world, is lowered to the seabed. The cutting tool uses its 24 water jets set at different angles to blast a trench through the clay. Suspended above is the 4-ton jet prop. The propeller draws in large volumes of the surrounding seawater, driving it at a high force towards the seabed, clearing debris from the trench. Transponders mounted on the sea floor relay a 3D picture of the operations to the control ship. And following along the entire operation, like a foreman on a job site, is an ROV that surveys the trench and confirms that it is dug to specifications. The battle of the clay is finally won. But when they start to lay the pipeline on the seabed, the problems really begin. The seabed under the North Atlantic is a tortuous and irregular landscape. There's over 1,000 kilometers of terrain like this along the pipeline route from Norway to England. It's so rugged that only small sections of these heavyweight pipes will actually make contact with the seabed. It's called free spanning, and they don't want it. It means the unsupported sections of pipe will sag, stress, and then break under their own weight. This would be an environmental catastrophe. They have to find some way of flattening out the pipeline route.
If you're not able to plane the seabed flat by moving the earth out of the way, you may have to fill in some holes with rock or other fill material.
They level the pipeline route by laying gravel down on the sea floor. This ship loads gravel into its cargo holds and delivers it to the area that needs leveling. It can carry over 9,700 tons of gravel at a time. Once at the job site, it uses a flexible fall pipe to place the gravel on the pipe pathway. Computers create a 3D model of the seabed and the path where the gravel needs to be placed. This method allows the crew to place the gravel precisely where they need it.
At these sort of water depths, you've got a problem because you haven't got that degree of control. I mean, whatever's doing the work down there is a huge distance away from the mothership, and they've got to still present a flat, smooth profile for the pipeline then to be laid upon. The other thing that has to be worried about is that you have to do that profiling as close as possible to the time that the pipeline is going to be laid, because Mother Nature tends to move things around again after you've left. And so you come back in a couple of weeks later and you find there's been a storm or whatever, and what you've taken so much care to flatten out has all of a sudden been moved around again. So you would lose the work that you've done before.
The pipe laying itself is a monstrous job. Once the pipe has been manufactured, it is placed onto the supply ships for delivery to the pipe-laying barge, the LB200. The barge is huge, longer than 2 football fields. It's an enormous floating steel welding factory, which has to work with military precision. There are only 3 of this type of ship in the world, and Hydro is using 2 of them here.
Pipeline route has been surveyed before we ever came here. We have ROV boats.
Ini adalah kapal untuk masang pipa bawah laut, pipe lebar, cukup panjangnya 2 kali panjang sepak bola. Cuma ada 3 di dunia katanya nih.
Boat just stands by with us. It monitors the pipe as it touches seabed, and it's a predetermined route that we follow.
The barge has been used in the Gulf of Mexico, in the Mediterranean, and off the coast of West Africa. But this is its biggest and most historic assignment. Once the pipe-laying process starts, it cannot stop. Not for weather, for accidents, for anything. The pipeline is built as a continuous tube that is dropped from the ship to the seabed. If the ship halts for too long, the strain on the pipe could snap it. The barge moves along at 4 kilometers a day and needs a constant supply of pipe sections, which must be delivered in the order in which they are to be connected and laid down. It's 100,000 pieces of pipe laid down end to end in a predetermined pattern.
They get moved by crane 3 or 4 times and go through about 15 or 20 welding stations and coating stations.
The pipe sections are delivered to the assembly floor, deep inside the LB200. Here, the welders are divided into teams. Their job is to create sections of the pipe called double joints. These double joint sections are 24 meters long. There's a lot at stake. The pipes have to be put together so there's no chance of leakage, and the assembly line has to keep up a steady pace. The entire operation is monitored by engineers who have video cameras that put eyes on the process, both inside and outside the pipe.
It's incredible technology, but the fundamentals are very simple. The fundamental thoughts that go behind it, because it has to be so rugged and it has to work every time, first time, that the actual basic engineering is still fairly simple.
The next stage of the assembly line is to join this short section of pipe to the main pipeline. It's being fed out of the back end of the ship and onto the sea floor. It's a complex process that requires a lot of fine-tuning. This is no ordinary welding operation. The process involves a special welding machine with 8 heads per station.
Ini proses pengelasan ya, antar pipa ya.
Passing through each of the welding stations in 7 minutes, the pipe is then checked by an ultrasound machine. If a flaw is detected, it has to be repaired immediately before moving to the next station. The process cannot be stopped. The connection has to be perfect, because this is the stage that welds them together forever. The assembly line is manned by industrial workers from over 30 countries. Shifts work around the clock to keep the assembly moving 24 hours a day. Each day, the teams have to assemble 3 to 4 kilometers of pipeline and drop it to the sea floor. After all the welding stations have linked the pipe, the final step of the operation is to seal the exposed metal. It is covered in a protective heat-shrunk plastic. Without this, the steel pipe would corrode in the seawater. Now, for the most critical step of the operation, offloading the pipe to the sea floor. The section where the pipes are joined is covered in foam to protect the welded joint during the drop. The decks are cleared and the pipe is now ready to be committed to the sea floor. A rubber tensioner grips the pipeline and holds it in place as it slides off the barge. As the pipe enters the ocean, it begins to sag and pressure is put on the entire pipeline, which is free hanging beneath the ship. Without exactly the right tension, the pipe could snap like a matchstick.
The pipe comes off the back of the barge in what's called a lazy S configuration. So it comes off the back of the barge and trails down to the seabed some distance behind. That S of unsupported pipe has to be kept from just buckling under its own weight. So to keep it under control, you've got to keep that under a huge tension to stop it from just collapsing under its own weight.
As the pipe is lowered, the barge moves forward 24 meters, not a meter more. With this well-oiled operation, the LB200 is able to lay over 100 kilometers of pipeline a month, as long as the pathway is clear. And clearing that pathway is a complicated process. In these particular sections of the pipeline route, they need a 2-meter deep trench. So they bring in the massive Sistem plow. This is the PL2. It's being used for trenching in shallower waters. It drops onto the seabed over the 1-meter diameter pipe, where its strong clamps pick it up. Then, as the surface ship pulls it forward, the plow cuts a trench 5 meters wide and 2 meters deep. To fill the trench, the BPL-2 follows behind with backfill to cover the pipe with a protective coating of sand. Early in the design phase, it was decided that they would bring the gas from the Ormen Lange field to the processing plant at Nyhamna, and then build another 1,200-kilometer pipeline to Britain. At the 600-kilometer mark, the line is broken and connected to the Sleipner riser platform. The Sleipner platform works as a hub, monitoring the 70 million cubic meters of gas flowing into the UK every day. But tying the pipeline into the platform creates a whole new set of engineering headaches. The underwater robots can line up the pipeline and the connecting pipes coming from the platform. A massive underwater crane moves them into position. But when they're matched up, there is no technology for replacing human beings in making the final connection. So the welders have to also become divers.
You ready to come down? Your hose good? Okay, he's ready to come down. Thank you.
It's just that these welders are working on the sea floor. Like working on the moon, the divers move around in pressurized modules to the work site.
Do one lift on it and see if we can rotate it into its proper orientation with you guys. Oh. Hey, you're clear of that, Dearman?
Here, new edges have to be cut and beveled at each pipe end before the welding hub is lowered onto the joint to connect the two sections. The welding habitat is dropped to the ocean floor. It has to be maneuvered in place perfectly over the 1-meter diameter pipe. It clamps the pipe and then closes itself off. The habitat is pumped full of air, forcing the water out. Topside, the dive supervisor uses cameras to keep a close eye on them and watch for any danger. Once it's safe, the divers move from the module to the welding habitat. Within this habitat, the diver welders make the final, permanent connection. It's a tricky and dangerous procedure. The welders are conformed halfway from normal spots and breaks. They look pipe past, known as the pig. This is the first of many underwater welds that they'll need to make all the pipe connections to get the gas flowing. 600 kilometers of pipe still have to be completed. But a major goal has been achieved with this connection. Now that the pipe has been sealed and connected, it has to pass inspection before they commit it to the next 40 years of service. This is done with the pipeline internal gauges, also known as the pig. It makes the epic journey through the entire pipeline, looking for weak spots and breaks. It also scrubs out the crud and salt water. Once in Easington, it emerges and the data is analyzed. The pipe passes inspection, and the team moves on to the next phase, which is getting the pipe onto land and into the gas plant at Nyhamna. But landfall is blocked by a surprise discovery. A mysterious shipwreck has been found 500 meters off the coast, lying in their path, and there is no way around. Marek Jasinski is retrieved. The archaeologists can define the coast, then brought out of the Ormen Lange
into play that we had no answer
after erosion. Which is already slugs move through the pipe, a labyrinth of pipes. This mega-sized natural, its job comes to an end at the top of the Storegga slide. This is the most demanding part of the entire Ormen Lange project. The steep terrain left in the wake of the Storegga landslide requires a special pipe-laying ship. This is the S7000. It's a former crane ship. It's been modified with a 130-meter tower on its stern deck. It's taller than a 33-story building. It's a floating factory. And it's so big, one can easily forget it's 100 kilometers in the tower and deliver full production under the North Sea.
Jadi itu kurang lebih ya pemasangan pipa bawah laut untuk gas terpanjang di dunia ya, the longest subsea pipeline. Oke. Khairul Sifa, are you there?
Iya, iya Pak.
Gimana? Ada pertanyaan nggak?
Belum ada Pak.
Apa? Belum ada?
Belum ada.
Oke. Jadi ketika kamu lihat barusan video apa tadi?
Tentang pipeline gitu Pak.
Pipeline, Pak, isinya apa? Gas atau minyak? Khairul. Isinya gas atau minyak?
Pak.
Isinya gas ya. Oke. Gasnya digunakan untuk apa di Inggris, di England? Khairul.
Untuk power plant.
Pembangkit ya, power plant ya. Oke. Terus dalamnya berapa pipa itu dipasang kira-kira tadi?
Gimana Pak?
Kedalaman lautnya berapa?
3 kilo.
3 kilo, tapi mungkin saya cek lagi itu 3 kilo atau 1 kilo ya, 1000 meter ya. Ada yang bagian 3 kilo, ada yang bagian 1000 meter ya. Ya, dalam nggak tuh?
Iya Pak.
Oke, ada nggak di Indonesia ada nggak ya seperti ini, operation seperti ini di water? 1000 meter, 1500 meter ada nggak? Hah?
Ada sih Pak.
Kenapa?
Ada.
Di mana?
Di Kalimantan.
Di mana sebelah Kalimantan apa? Proyek apa namanya?
Ini IDD Pak, Indonesia Deepwater Development.
Oke. Indonesian Development Project ya, IDP ya?
Iya.
Bloknya apa namanya?
Apa Pak?
Blok yang punya siapa Pak? Blok gasnya yang punya siapa?
Chevron.
Chevron. Oke ya. Jadi sekarang banyak penemuan baru itu di Indonesia Timur, which is itu bloknya itu adalah di water semua gitu ya. Ya, oke. Oke, ada pertanyaan nggak? Kalau nggak kita mulai lagi dengan kompresor ya. Kompresor. Ini bisa nggak? Oke. Ini udah kelihatan ya? Slide-nya udah kelihatan? Halo? Khairul?
Kelihatan Pak.
Oke.
Iya.
Oke, sekarang minggu lalu tentang pump, ini sedikit 10 menit tentang kompresor. Jadi fungsi kompresor memperkecil volume gas, screen. Memperkecil volume gas, menaikkan tekanan, temperatur dan densitas gas meningkat ya. Ini kompresor. Nah ini bagi dua, ada yang intermittent flow dan ada continuous flow. Ya, ini positive displacement sama seperti kayak pompa. Nah, positive displacement ini ada reciprocating, ada rotary ya. Kalau reciprocating ini pakai mechanical piston, kalau rotary tadi pakai vane, liquid piston atau loop. Ya, loop ini ada helical, ada straight loop ya. Kalau continuous itu ada ejector, ada dynamic. Dynamic ini ada radial, axial, mixed flow, centrifugal, radial flow ini centrifugal, axial flow ini axial, mixed flow ini mixed flow. Ya, talk about kompresor ya. Tadi kalau gas tadi 1.200 km kita nggak tahu apakah ada menggunakan kompresor nggak kira-kira ya. Rasanya mesti ya ada kompresor station gitu ya dari Norway sampai ke England. Nah itu kamu bisa cek di Google kira-kira ada berapa kompresor pada pipa sepanjang 1.200 km. Oke, intermittent flow, positive displacement kompresor. Merangkap gas dalam ruangan dalam kompresor, volume dikurangi, dengan mengurangi volume, of course, pressure meningkat. Rasio tekanan tinggi sekitar 200, dan laju alir volumetrik sampai 1.000 kubik meter. Ya. Jenisnya bisa reciprocating piston, dan rotary kompresor. Kalau continuous flow mengubah energi kinetik menjadi energi tekanan statik disebut dynamic kompresor, digunakan untuk laju volumeter sampai dengan 1 juta kubik meter dengan rasio tekanan moderat ya 20. Artinya P discharge dengan P suction 20 kali ya. Kalau positive displacement kompresor itu bisa 200 kali ya. Oke. Ini centrifugal kompresor. Bentuknya seperti ini ya. Seperti turbin ya di pesawat ya, pesawat jet. Besok kita lihat animation ya. Nah ini how does a centrifugal compressor works? Ya. Turbo centrifugal compressor are used to elevate gas pressure for several reasons, including the transmission of gas in a pipeline. Jadi itu pipa transmission ya, yang panjang-panjang besar. Tadi diameternya berapa tadi pipanya? Ada ingat nggak? Devina, Valencia, are you there?
Iya, Pak.
Tadi pipa yang di Laut North Sea, diameternya berapa meter?
Saya rada lupa, Pak, kalau diameternya.
Kira-kira? Just guessing.
Lebih dari 5 meter, Pak. Nggak tahu juga sih, Pak.
Oh, diameter, lebarnya. 5 meter itu satu rumah sampai atap 5 meter ya. Ada yang tahu? Muhammad Farhan?
Ya.
Diameter pipa tadi berapa tadi dari Norway ke England?
1.200 Pak.
Panjangnya. Ini diameter pipanya.
Kurang tahu Pak.
Tadi ada yang tahu? Joshua Martona?
Hadir Pak. Kalau saya lihat di Wikipedia sekitar 34 inci Pak. 34 inci atau 0,86 meter gitu.
0,8. Itu yang dipakai di itu ya? Tadi ya, pipa Norway England ya?
Iya Pak, Norway.
Tadi kalau nggak saya lihat itu 1 meter dia bilang sih. Jadi kalau 38 inci kali 2,5, 0,8 ya? 0,8 meter ya? Oke. Ya udah oke. Ya kurang lebih lah ya. Itu 1 meter atau 80 cm itu termasuk pipa transmission ya, yang gede-gede, yang panjang ya. Sumatera, Singapura. Terus Kalimantan Jawa ada nggak ya Kalijaya? Udah jalan belum ya? Saya lupa ingat. Ada nggak pipa nyambung pipa gas dari Kalimantan ke Jawa? Nah, tapi ini dari Norway ke England. Ya. Jadi for several reasons, including the transmission of gas in a pipeline. the reinjection of gas in formation to improve oil production and to facilitate chemical processes. Their contribution eventually lead to the production of specific end products such as gasoline, plastic, chemical, or fertilizer, to name a few. Outline here is typical syngas centrifugal compressor and the processes that take place with it. Ya, ini 1 sampai 11 ya. 1, at the inlet, low pressure gas enter from the customer's process. Ya. 2, the inlet wall, ini 2 ya, sini ya. The inlet wall and inlet guide fan distribute gas flow evenly to the first stage impeller. 3, the first stage impeller, 3 itu ini ya, yang warna ungu nih ya, first stage impeller is attached to the shaft. Ini shaftnya kali ya. Ya, ini shaftnya. Shaftnya itu apa ya? AC ya. Rotate at a high speed, accelerating the gas and imparting kinetic energy to the gas in the form of velocity and the potential energy in the form of pressure. Jadi dia dengan adanya rotation ini dia meningkatkan kinetic energy dalam bentuk velocity kecepatan dan potensi energi dalam bentuk pressure. 4, diffuser, ini diffuser nih, yang bolong ini. The diffuser continues to change the kinetic energy of the gas velocity into potential energy pressure. 5 ini ya. The return band and return channel remove the tangential velocity component from the gas and further delivery of the gas to the second state impeller of optimum condition. 6. Step 2 and 5, 2 sampai 5 are repeated at the other stages until the required discharge pressure is achieved. Ini ya. 1, 2, 3, 4, 5. 2 sampai 5. 7. At the recycle gas inlet, the syngas compressor that make up that is joined with the recycled gas. Ini adalah recycle ya. At the recycled gas inlet of the syngas compressor, the make up gas is joined. Ini make up, itu masukin make up gas. The side stream plenum area allows the make up gas and the recycled gas to mix and enter the recycle impeller. 9, ini recycle impeller accelerate both the make up gas and the recycle gas imparting velocity. Ini connect to the driver motor. 10 is final diffuser and discharge fluid continue to convert velocity into pressure and prepare the gas for return to the customer process to the discharge nozzle. 11, the gas leave the compressor at the discharge nozzle and return to. Jadi ini si customer mau meningkatin pressure. Nggak nyala nih. Wait. Bentar ya. Next, oke. Seperti pompa, ini kompresor juga punya curve ya, performance curve ya. Tapi di ini adalah koordinat adalah isentropic head, ya, isentropic head. Satuannya feet pound per feet pound per pound ya. LBF per LBM. Apa tuh LBF per L? Ada yang tahu nggak? Jadi LBM pound mass, LBF adalah pound force ya. dalam English system. Ya. Jadi feet pound force per pound mass. Ini adalah inlet volume flow ya. Cubic meter. Oke, ini yang ini adalah performance kompresornya, semakin ke atas semakin tinggi, RPM-nya semakin tinggi ya. 10.000, 11.000, 12.000, 13.000, 14.000, 15.000, 15.700. Ini adalah kurva isentropic efisiensi. Ya. Isentropic efisiensi ya. Jadi isentropik itu adalah entropinya konstan ya. Oke. Kemudian ini adalah ratio of specific heat, specific gravity, suction temperature, and suction pressure. Ini ada surge limit. Apa nih artinya surge limit? Kalian tahu nggak? Ikrimah, Elyasa Bahalwan, are you there? Ya, Ikrimah. Ini ada sebelah kiri ada line surge limit. Kira-kira tahu nggak kamu apa maksudnya?
Surge limit.
Ya, cek coba kamu di Android atau di Google.
Kayak tekanan, Mbak. Batas tekanan itu.
Batas tekanan artinya apa? Apakah kita bisa bekerja di sebelah kiri surge limit?
Seharusnya enggak.
Enggak ya. Jadi pada surge limit flow-nya ini terlalu rendah sehingga kadang-kala pressure di discharge itu lebih tinggi ya di receiving. Akibatnya bisa terjadi flow kebalikannya. Ya, tadinya dari kiri ke kanan, di suction ke discharge, karena adanya surge ini, ya limitation ini, dia malah balik dari kanan ke kiri, dari 2 ke 1, dari discharge ke, jadi kita nggak bisa kerja di bawah ini. Terus Ikrimah, ini ada 78, ada 78. Ini maksudnya apa nih? Efisiensinya. Ini kan 78.
Iya, Pak.
Ini juga 78. Kira-kira kenapa ada 2 garis itu?
Itu kayaknya yang garis isentropi. Nah.
Ini nyambung ya?
Kalau yang satu lagi.
Ini nyambung nggak kira-kira nih? 78 ke sini nih. Bentuknya mirip ini nggak ya 80%?
Ya, harusnya nyambung. Kalau
nyambung ya. Jadi kalau kamu beli kompresor, kalau bisa ada di yang 80% ini. Semakin ke kanan, ya ini semakin turun efisiensinya. Ya sebetulnya di sini ada disebut dengan stone wall ya di sini ya. Jadi kayak dicekek gitu ya. Jadi pressure-nya terlalu tinggi, volumenya terlalu tinggi sehingga kayak dicekek gitu loh, saking tingginya. Nah, ini disebut stone wall. Ini kita juga nggak boleh kerja di luar stone, di sebelah kanan dari stone wall ya. Oke, makin ke atas RPM-nya, makin tinggi tekanannya, makin tinggi juga RPM-nya. Oke, ada pertanyaan nggak? Kalau nggak ada, untuk hari ini kita coba selesai gitu ya. Any questions? Catherine, Andera Silangit.
Belum ada, Pak.
Oke ya, saya mohon kamu pelajari ini, mengerti tentang kompresor curve ini. Ya, intinya kita kompresor ini nanti juga harus untuk dipakai untuk melawan energi operation lain juga ya, ada friction dan lain-lain. Ya. Oke, kalau nggak ada, Pak Wawan, ada menambahkan?
Tidak ada, Pak.
Nggak ada ya? Oke. Terima kasih semua ya. Jangan lupa absen. See you later. Jaga kesehatan ya. Oke, selamat pagi. Assalamualaikum warahmatullahi wabarakatuh.